All right, let's pull back the curtain on something you probably do dozens, maybe even hundreds of times a day without even thinking about it. We're going to uncover the secret life of a simple terminal command. So you're at your command prompt. You type something like echo hello. You hit that enter key and poof, hello appears. Seems instant, seems simple, but what really just happened in that tiny fraction of a second? Well, let me tell you, that single keystroke kicks off an absolutely epic journey. It's a whirlwind adventure that dives deep into the core of your operating system, crossing protected borders and even changing its own identity. And today, we're going to follow it, step by step. Okay, first things first, you got to understand the lay of the land. Your operating system basically has two worlds. You've got user space, that's the friendly neighborhood where all your apps live, like your browser and, yeah, your terminal shell. They can't just do whatever they want. And then you have kernel space. Think of this as the high-security, all-powerful control room. It's the core of the OS, and it has total control. Our command's entire journey is about traveling between these two worlds. So, here's the roadmap for this little odyssey. It all starts with cloning, then a complete transformation, then it actually does the work, and finally, a graceful exit and cleanup. Sounds like a movie plot, right? Let's dive into Act 1. All right, you've hit enter. The first thing that happens is your shell, which is just another program hanging out in user space, reads what you typed. It figures out, okay, they want to run the echo program, but the shell itself can't do that. It needs to ask for help from the big boss, the kernel. And how does it ask for help? With something called a system call. Think of it like knocking on the kernel's door with a very specific, formal request. The very first request is a system call named fork. This is its first leap into kernel space. And what it's asking is kind of weird. It's telling the kernel, hey, can you make a perfect clone of me right now? And the kernel obliges, creating what's called a child process. Now, once it's inside the kernel, this whole cloning thing is ridiculously efficient. The kernel gives the new clone its own unique ID. But here's the brilliant part. It doesn't actually copy all of the shell's memory. That would be slow. Instead, it uses a clever trick called copy on write. They just share the parent's memory until one of them tries to change something. It also copies the connections for input and output, and finally puts this brand new process on the scheduler's giant to-do list. So now we have two shells running, our original one and its brand new clone. But we don't want another shell, do we? We want to run echo. This is where things get really interesting. It's time for the great transformation. That new child process, the clone, immediately makes another system call. This one is called execve, and this request is just wild. It basically says, hey, kernel, you know me, this clone of the shell. I need you to completely wipe me out and replace me from head to toe with a totally different program, the one called /bin/echo. It's a software identity swap. And the kernel is like, you got it. It acts like a bouncer, a demolition crew, and a stage manager all at once. First, it checks, are you even allowed to run this? Security first. Then, it tears down the old memory space of the shell clone. It loads the actual code for the echo program right off the hard drive, sets up a fresh new workspace for it, puts the hello argument in there, and finally points the CPU right at the first instruction of the echo program and says, action. And just like that, the transformation is complete. The process that was born as a shell clone is now, for all intents and purposes, the echo command. Its whole identity has changed. So now, finally, it can do the one thing it was created to do, print hello. But wait, you'd think it could just write to the screen itself, right? Nope. One more trip to the kernel is required. See, you can't have random programs scribbling all over your display. That would be total chaos and a huge security risk. So to do its job, the echo program makes another system call, write, and politely hands the string hello over to the kernel, saying, could you please put this on the screen for me? Now, while all of this is going on, and we're talking microseconds here, don't forget your computer is juggling 1,000 other things. The kernel's scheduler is like this master conductor of an orchestra, giving Echo a tiny slice of CPU time, then your music player, then your browser, switching between them so incredibly fast that it feels like everything's happening all at once. It's an amazing balancing act. So, hello is on the screen. Mission accomplished. The Echo command's life purpose has been fulfilled. But the story's not quite over. You can't just leave a mess behind. It's time for the final act, the grand finale. So for its final performance, the echo process makes one last system call, exit. It's basically raising its hand and telling the kernel, hey, I'm all done over here. everything went great by sending back an exit code of 0. And this kicks off the cleanup. It's a really neat little process. The kernel marks the finish process as a zombie. Yeah, really. It's not running, but its exit status is preserved. Then, the kernel sends a little signal, kind of like a text message, back to the original parent shell. The parent shell then calls wait to read that exit status and acknowledge its child is done. Only after that happens does the kernel finally sweep in and reclaim all the memory and resources. The cycle is complete. So when you look at the whole thing, this entire journey is really a story about these carefully controlled trips back and forth between the regular user world and the super powerful kernel world. Each one of those system calls, fork, execve, write, exit, is like a guarded portal. And that separation, that strict control, is exactly what keeps our computers secure, stable, and able to do so much at once. Now, I know what you might be thinking. Whoa, that is a ton of work just to print hello. And you know what? You're right. It is. But this intricate, beautiful dance is the absolute foundation of how modern computers work. This whole process is why everything works so well. It gives us security because one badly written program can't just reach out and crash the entire machine. It gives us stability because the kernel makes sure everyone plays fair with memory and CPU time. It makes programming easier through abstraction. And of course, it's what lets thousands of things appear to happen at the exact same time.